Welcome to this explainer. Today, we're not just digging into some basic neural network layer. Nope, we are stepping right into the shoes of systems architects. We're going to figure out how to actually design safety, nuance, and probability directly into artificial intelligence. We are talking about the architecture of ambiguity, specifically through the fascinating lens of mixture density networks.
Okay, let's kick things off with a pretty foundational engineering question. What exactly happens when your standard neural network runs into a situation where a single input validly results in completely different yet equally correct outputs? We call this a one-to-many mapping problem. And honestly, it's a situation that fundamentally breaks all of our traditional machine learning assumptions. When you put the standard approach and our solution side by side, the difference in philosophy is just staggering. A standard regression network acts a lot like a dictator, right? It demands that there is exactly one correct answer for any given input. So if the real world is ambiguous, it just stubbornly outputs a mathematical average. A mixture density network, or MDN, on the other hand, acts more like a weather forecaster. It doesn't force one rigid number on you. Instead, it outputs a probabilistic forecast of different scenarios, each with its own specific level of confidence.
Let's move to Section 1, the flaw of averages. To really grasp why this architectural shift is absolutely crucial, we have to look at the inherent flaw of mathematical averages when we apply them to physical systems. The history here takes us back to 1994. A researcher named Christopher Bishop was trying to solve a classic engineering challenge, robotic inverse kinematics. So imagine a two-joint robotic arm. If you want that robot's hand to reach a specific target spot on a table, there are usually two completely different, perfectly valid ways to get there. You can reach the target with the robotic elbow pointing up or with the elbow pointing down. Two perfectly valid answers for one single input.
Well, Bishop initially trained a standard neural network on this data using mean-squared error, or MSE. Now, because MSE literally forces the network to find a single compromise, the network output the exact mathematical average of the elbow up and elbow down angles. The physical result of that? The prediction corresponded to a position where the robotic arm would literally have to snap in half to reach the target. Not exactly a great day for the robot, right? It was mathematically correct on average, but a total mathematical impossibility in physical reality. And it's this exact catastrophic failure that forces us to upgrade our output layer.
Section 2. The probabilistic recipe.
So, to design an architecture that can actually handle this kind of uncertainty, enter the mixture density network. This is a fundamental architectural shift. The backbone of the neural network stays exactly the same, but the output layer is entirely transformed. Instead of spitting out a single, highly flawed point estimate, it's designed to output the parameters of a full, nuanced probability distribution.
And this brings us to our probabilistic recipe. Think about predicting your commute time. Instead of giving you a single wrong guess, the MDN maps out actual scenarios. It might output scenario A, a 30-minute commute, high confidence, 60% probability weight. Scenario B, a 60-minute commute because of a minor accident, so there's a wider, lower confidence spread, maybe a 30% weight. And scenario C, a 120-minute highway closure, high confidence, but only a 10% weight. It's handing you the exact mathematical recipe to draw a multi-humped probability curve. Now, this is honestly the visual aha moment of the whole concept. Notice the inverted U-shaped data scatter here. It's a classic one-to-many problem, where the middle of the x-axis has valid data points at both the very top and the very bottom of the y-axis. Now, a standard network would just draw a useless line straight through the empty space in the middle. But watch this bright line graph overlay for the MDN. As the model learns, you can literally see the graph dynamically pulling from a single average bump, morphing and separating into two distinct, separate humps that perfectly align with the actual data scenarios. The network is physically learning to isolate ambiguity. It's incredible.
Let's check out Section 3, the code math sync. All right, how do we actually build this? To see how this builds the bridge between complex mathematical theory and practical code, we have to look at the variables. To generate those humps, the neural network outputs the parameters for a Gaussian mixture model, and this relies on four core variables. First up, K is your architectural choice. That's the maximum number of mixture components, or humps, you want to allow. Second, pi is the mixing coefficient, which sets the weight or likelihood of that specific hump. Third, mu is the mean, setting the exact center location. And finally, sigma is the standard deviation, representing the width or the uncertainty of that hump.
This code math sync shows exactly how we translate those theoretical variables into PyTorch, overlaying the math symbols right next to our variable names. We map the math symbol pi to pi logits, which absolutely must pass through a softmax activation, so all those scenario probabilities sum perfectly to 1. We map mu directly to the mu tensor with a linear activation. No changes needed there since the center can be any real number. And crucially, we map sigma to a sigma underscore pretensor that has to run through an exponential activation function. Why? Because standard deviation, representing our uncertainty, mathematically must be strictly positive.
But implementing this brings up a massive computational hurdle. When we calculate our negative log likelihood loss, we have to sum up Gaussian probabilities. In high dimensions, these probabilities get microscopic. We're talking 10 to the power of negative 50. If you try to sum those in standard floating point arithmetic, the computer just rounds it to exactly 0. And taking the log of 0, that crashes your entire system with a nan, not a number. As systems architects, we bypass this by using the log sum exp trick. This performs the addition entirely within logarithmic space to prevent catastrophic underflow. But even with stable math, we still have to design safety directly into the behavior of the architecture itself.
Which brings us to Section 4, Engineering Safety Belts.
The crucial point here is ambiguity management. We absolutely have to prevent degenerate solutions from ruining our model. Watch this timeline of the fatal sigma collapse bug. By epoch 10, one of our Gaussian humps manages to center perfectly on a single data point. Great, right? Well, by epoch 20, the network realizes it can artificially decrease the loss by making that hump thinner and thinner. By epoch 30, sigma approaches 0, and the hump becomes a sharp, impossible spike of infinite density. By epoch 40, the model thinks it's receiving infinite reward, the loss line shoots straight to infinity, and your training completely crashes.
And that right there proves why clamping sigma isn't just some stylistic choice, it is a mandatory engineering safety belt. We must enforce a minimum value like 1e3 to prevent sigma from ever hitting 0. We also have to use careful initialization and label smoothing to prevent something called mode collapse. That's a bug where the network gets lazy, assigns 99% of the weight to just one hump, and effectively degrades right back into the dictator-like standard network we were trying to avoid in the first place.
Section 5. Modern architectural connections.
So, where does this specific architecture actually fit into the broader modern landscape of AI? From robotic arms in the 90s, MDNs have evolved into the true backbone for AI systems navigating the physical world. In autonomous driving, for instance, they are essential for predicting whether the car ahead is going to brake, swerve left, or swerve right, giving us probabilities for each trajectory. In reinforcement learning, continuous control policies use them to sample different actions so a robot can safely explore its environment. And over in finance, they're used to model regime-dependent volatility, capturing the massive sudden shifts between bull and bear markets. However, it's just as important to know where your tools fail. You might be wondering, why don't we use MDNs to generate high-resolution images like Midjourney does? The simple answer is parameter cost. An MDN predicts the entire multi-modal distribution all at once. If you tried to predict a high-dimensional image with just 10 mixture components, you'd need millions of parameters purely for the final output layer. It's just way too computationally heavy. That is exactly why the industry shifted to diffusion models for images, which cleverly break the high-dimensional problem down by predicting at tiny conditional Gaussian step one at a time. One quick architectural distinction before we wrap up. It's vital to separate MDNs from other multi-component buzzwords you might hear, particularly mixture of experts or MO, which is used a lot in modern large language models. MO is entirely about routing compute. It sends tokens to different network weights to save processing power, all while still outputting a deterministic answer. A mixture density network does not route to different weights. It uses the entire network simultaneously to model the fundamental uncertainty of the universe, outputting the exact parameters of a probability distribution.
Knowing the catastrophic flaws of standard mathematical averages and seeing just how effortlessly an unconstrained model can collapse into impossibility, the question for you as a systems architect is super clear. How will you embrace and practice ambiguity management in your next deployment? Are you going to build a dictator, or are you going to build a forecaster? Thank you so much for joining me for this explainer, and I'll catch you in the next one.